Yeah. So our world is no longer is a kind of black and white. So there is a kind of different shades that we can think on the facts, right? So the facts, they are now probabilistic, and the propositions that represent the facts, they are now probabilistic, right? And as we will be using this probability, we'll be playing with probability a lot. So that's why I have created a video for reviewing the probability concepts and have shared that with you. I hope that you have seen that. But again, those are very basics on probability. I'll not be covering that in the class. So if you want, you can revise the concepts by looking at the video, or you can have it from the other places as well. So I'll start with probability concepts that are very important to us, and we'll be using those concepts very frequently as we go forward with our objective of reasoning with uncertainty. Just give me a cue whether you can see my slide or not. Slide is on independence. Anyone?
Yes, sir, visible.
Okay. So let's say what we are interested in. We are interested in to compute the joint probability distribution for a set of random variables. So that we have discussed earlier. So basically what we have this set of propositions like alpha 1, alpha 2, alpha n, and we want to see what is the joint probability of these variables. And this proposition can either be true or false, right? So you can assign many values to it, right? So for example, you can assign alpha 1 to be true, alpha 2 to be true, and alpha n to be true. So that is a kind of assignment. And that assignment gives you a possible world. And in probabilistic notion, every world is probable. Some world is having higher probability, and some other world they are having lower probability. But the point is, every world described by different combination or different assignments of the values to the propositions, we have a probability assigned to that, right? Now, if you think of to fully specify this joint probability distribution, we have this order of 2 to the power n assignments. That I think you agree with me, right? And you see, this is not really tractable if you have, say, thousands of variables, right? So the complexity of processing this and representing this will be very high, right? So that's why what we do, we assume some events to be independent. And this we do in two objectives, with two objectives. First objective is that some events are not truly dependent on each other. So we'll have examples of those kind of events or pairs. And the second reason is that to make the computation more efficient. So as I mentioned, that fully specifying this joint distribution is not really tractable. So if we somehow assume that some events are independent, we'll see that we can gain much in terms of efficiency. So we do not need to compute every possibilities, every assignment. We'll be just happy to compute a subset of the assignments, and that will serve our purpose. So let us talk about a formal definition of what we call as independence. So let's say we want to define the joint distribution of two variables, two random variable x and y. So this capital X and capital Y, they are our random variables. And these small x and small y, they are kind of different values that we can assign to random variable x. So for example, if you say roll of a dice, so that is a kind of random variable. And for say what is the probability of the outcome, say the roll of dice will give you, say, value of 4, right? Now we say that two random variables are independent if the joint distribution between them can be represented as the factor of individual probabilities. That we know, right? And we represent that using this symbol. X is orthogonal to y, basically they are independent of each other. And corollary to that is we can say that the conditional probability x given y can be written as probability x because x does not depend on y and vice versa, right? Now, we say that independence is basically a simplifying modeling assumption, right? So we are just trying to simplify the computation of the joint probability distribution. But maybe the independence assumption that we are taking that may not be valid also. But you are making some assumption to make the computation more easy, right? So let us take an example. So let's say you have two random variables. One is, say, 2020 US presidential election result and your toothache. So these are the two variables. So this is your X and this is your Y. So by and large, you can say they are independent, right? But you see, these two variables may not be independent. Maybe by seeing the election result, you are so happy that your toothache is gone, right? But you see, that is a kind of very what do I say? Uh, I'll not say that is a very probable explanation of the relationship between these two random variables. In most of the cases, we'll see that these two variables are independent. So that's why we say this is a simplifying modeling assumption. Maybe they are not independent, but for the sake of simplicity, you see they are very distant to each other. So that's why you can treat them to be independent, right? Now, let us play with another set. We have got four variables. One is weather, traffic, cavity, and toothache. So we can safely assume that this weather and traffic, they are dependent on each other. Cavity and toothache, they may be dependent on each other, but these two set, they may be independent of each other. But again, they are kind of simplifying assumption. It may so happen that if you have rainy season, you might be having toothache, something like that. Right. Now, we need to have a very structured way to test whether two events are or two random variables are independent or not. So let us see how do we do that. So this is an example joint probability distribution of, say, P, temperature and weather. So the temperature can take different values and the weather can take different values. And we have specified the probability for all possible worlds. And that gives us this joint probability distribution between T and W, right? Now, what we can do, we can marginalize this joint probability distribution to get the marginalized distribution. So here we are trying to compute probability T. So this marginalization process, all these things have been described, discussed in the probability review video lecture. So if you don't understand this, I will ask you to follow that video. So basically here, we are ruling out the other variable W. So that is what we call as marginalization. So those who have not watched the video. So here we are trying to find what is the probability of hot and what is the probability of cold. And similarly, we can do the marginalization on T to get PW, right? Now, if these two events are independent, so I can reconstruct the joint probability distribution table from these two. How do you do that? So basically you can say PTW is equal to PT PW. So that's how we can do it, right? Now if you multiply this, so you'll be having these say P1 TW. So this is a kind of new joint distribution that I'm trying to get out of these two marginalized distribution, right? Now, how do you do that? So basically, I'll take this row and take this row and multiply the probability values, and it will give us 0.3. So you see that from this and this, these two tables are not really same. And then we can say that these two variables, they are not independent given this joint distribution, right? You can compute the others. They will kind of vary different from the original joint probability value. So that's how we can say whether two variables they are independent or not. Now, why independence is so important to us? So let us take into account an event where you have a fair coin and you are flipping the coin for n trials. So there are n trials and we are flipping a coin at every trial, and you have a probability of head and probability of tail. And so this is the probability of one trial. This is the outcome of another trial, and this is the outcome of the nth trial. Now, if you want to represent the joint probability distribution of these n number of trials, so what do you need to have? You need to have 2 to the power n assignments. So what maybe you have head all the time, you have a probability value. You have tail all the time, you have a probability, and in between you have different other assignments, right? But you see, if we assume that these every trial is independent of each other, then what we need to just specify, we just need to specify what is the probability of head or what is the probability of tail. So that means for every trial, how many assignments I have to make? I have to make only one assignment, because if I know the value of probability H from here, then I can compute the probability of T. So that's why we need one assignment here, we need one assignment here, and we need one assignment here. So in total, we need n number of assignments. So you compare n versus 2 to the power n. So we are gaining a lot here, right? But you see, we cannot really uh, have this assumption that all the variables are independent of each other. So this is a very, very simplifying assumption, and that is not really practical to see that all the variables are completely independent of each other. Some set of variables, they are dependent on each other, and some variables, they are dependent on each other given another variable. And that what brings us to the notion of conditional independence, right? So we say that two events A and B are conditionally independent given another event C. So how do we write this? So these two variables are conditionally independent of each other given another variable C, right? So when do we see that? So if we have this property, so the probability of joint probability of AB given C can be factored into probability of A given C multiply probability B given C. So try to compare this with the other formula like probability AB equal to probability A, probability B. So this was simple independence, and this is conditional independence where we have conditioned on the variable C, right? So that's what the difference is, right? Now, while we computed this conditional probability A given B, our computation was the joint probability given by probability B. So that's what the value that we get for probability A given B. So this is the formula for conditional probability, right? Now we can extend this by saying, well, we are conditioning on two variables, not a single variable, right? And we can rewrite this formula as probability A and B given C divided by probability B given C. And we know that this is a kind of, so this should be multiplied. So this can be refactored into probability A given C, probability B given C, and below you have got probability B given C, and what we have as an outcome, it is probability A given C. What does that mean? We are saying that probability A and B, they are independent of each other given C. So that means the conditional probability A given BC only depends on C. So I can safely remove this from our formula to get probability A given C, right? So let us have some examples on this idea of this conditional independence. So we have three variables. One is toothache, cavity, and catch. So toothache is whether you are having toothache or not. Cavity is whether someone is having cavity or not in the tooth. And catch is whether a probe by dentist is able to catch the cavity, whether there is a cavity or not. So these are the three variables, right? Now let us try to compute this. The probability of there is a catch. So when we say plus catch, so that means there is the probe is able to catch the cavity. So what is the probability that the probe is able to catch the probability cavity given you have got toothache and cavity? So my argument is that it is not really dependent on whether I am having toothache or not. So it depends on the precision of the device. And there will be a probability that if there is a cavity, then the probe will be able to catch it, right? So that means this whether I am able to catch there is a cavity or not, that no longer depends on toothache. So these conditional can be rewritten as probability of catch given cavity, right? With a similar argument, I can say probability catch given toothache minus cavity. That means there is no cavity, but again, in spite of that, the catch is saying that the probe is saying that there is a cavity. So there can be an imprecision in your device that might say that even if there is no cavity, you report that there is a cavity, right? And also that is independent of whether you are having toothache or not. So that means this can be simplified as probability catch given minus cavity. So in essence, what we are saying the random variable catch is independent of the other random variable toothache given that you have cavity, right? So we are saying catch is independent of toothache given cavity. And this is what we call as conditional independent. So as a corollary of that, we can do the reverse, like say, as catch and toothache are independent of each other, we can reverse the position of catch and toothache. We can say that probability of toothache given catch cavity is equal to probability of toothache given cavity. And of course, probability toothache and catch given cavity can be refactored into probability toothache given cavity and probability catch given cavity. And finally, we can say that toothache is independent of catch given cavity. Right. So there are other examples of conditional independence, and you can think of others. So amount of speeding fine and the type of car, they are independent of each other, given that you know the speed of the car, right? So you can say that lung cancer and ear teeth, they are independent of each other, given that you know the fact that the person is a smoker, right? So similarly, you can say that if you know the present, right, then the future and past, they are independent of each other. So this is how you write future and past. They are independent of each other, given you know the present. Right. So there is a very simple and very interesting test of conditional independence. So let us say we have three variables. X, you want to test whether X and Y, they are independent of each other given set. So how do you do that? So you imagine that you know the value of Z, right? And you are trying to guess the value of X. And let's say you have guessed it, right? Now, there is an envelope in which the true value of Y is written, and that is kept in your pocket, right? Now, after you have guessed the value of X and then try to bring out this envelope and open the envelope to see the value of Y. Now you need to check whether knowing the value of Y changes your mind of the assignment that you made on the value of X. So if there is no effect, then X and Y are independent of each other. If there is an effect, then X and Y, they are not independent, conditionally independent of each other. So this is a very interesting test that you can check later, right? Any question till this point before I move to the main content? Okay, so we talked about conditional independence, and this conditional independence is very useful when we talk about representing the knowledge of the world in a very efficient way. And that is being done using a particular data structure.
Sir, excuse me.
Yeah, yeah.
Sir, yes, sir. I was muted, so I was unable to speak. Sir, can you go to the previous slide?
This one,
Before that, sir.
this one.
And sir, before that one, before that.
This one.
Yes, sir.
Yeah.
Sir, here, like A, that what is that symbol? A and B given C. Is it like that?
Yes, A and B given C. So so we can write this in other notion like say A joint B given C. So as we are talking about knowledge bases, so in our knowledge base, we represent the knowledge base as say you have different facts like A, B, and C, right? So we are following these format. So these two are same, these and A and B given C. These two are same.
Okay. And sir, in the third line, A given B comma C means A given B and C. Is it like that?
Yes.
Okay. So how are we expanding it like that? Means we are taking A and B then given C. I did not understand this part. Like,
so actually these are coming from the probability axiom. So I will not be able to cover this here. So
okay, sir.
So basically you have a similarity between these two. So you try to correlate these two. So here we are conditioning with another extra variable C, right? So how do you write this A condition B? You are writing A condition B to be A and B divided by probability B. Here we are conditioning with another variable C. So we are just rewriting this with this new condition. That's it.
Okay, sir. Got it.
Right?
Yes, sir.
Any other questions? Well, so let us talk about the data structure that we'll be using to implement the idea of making the inference more efficient or representation more efficient. And that is being done by this Bayesian network. And in other term, it is also called Bayesian belief network because this network represents the belief of the agent in an uncertain world. So this is also called Bayesian belief network, or BBN in short. So we'll be using both the terms, right? So again, let us try to revisit the conditional independence and its relation to the probability chain rule, right? So what we are interested in, again, we are interested in this joint probability distribution, and we know that it is having 2 to the power n assignments, right? Now, we can factor this joint probability using the chain rule. You know the chain rule, like you have this probability of x1, probability x2 given x1, and finally probability xn given x1, x2, xn minus 1. But it's see that we have factored these into different probability values, but yet it is in the order of 2 to the power n, right? Because here you need to have all possible assignments on n minus 1 variables. And that brings us again to order of 2 to the power n assignments, right? So we need to do better. How do we do better? We make some conditional independence assumption. So what conditional independence assumption we can make? So this is one conditional independence assumption, but you can make others. So you're saying that xi given xj xk is same as probability xi given xj. So what does that mean? That means that xi is conditionally independent of xj given xk. Sorry, conditionally independent of xk given xj, right? Now, if we plug in this assumption here in the chain rule, then what we get? We get this expression to be probability x1, probability x2 given x1, and finally probability xn given xn minus 1. So this is a kind of very simplifying assumption that one event is, or one variable is dependent only on the previous variable. And that is what we call as Markov assumption. But again, this is another kind of simplifying assumption. We are just seeing that one variable is dependent only another single variable. But in general form, it might so happen that our variable xn is dependent on, say, x n minus 2, x n minus 1, something like that, right? So let us try to find a way to represent these kind of dependencies in our data structure. So let us take this example, rain traffic umbrella. So there is a rain or not, there is high traffic or not, and whether people are using umbrella or not. So we can say that this traffic and umbrella, they are conditionally independent of each other given rain, right? So that we can say. And from this, we can follow that the probability that people bring out umbrella given there is traffic and rain is only dependent on whether there is rain or not. It is not dependent on traffic, right? And similarly, we can write probability whether there is a traffic given umbrella and rain. It only depends on rain. So that's why you can rewrite this as probability T given R, traffic given rain. And probability U given R can be written as probability TR and probability U1. So this can be followed from the axioms that we have written earlier, right? Now, how do we represent that as a chain rule? So the simple chain rule will be giving us probability rain, probability traffic given rain, and probability umbrella given traffic rain. So this is what the simple chain rule, but we know that this can be equated as probability umbrella given rain, right? So we can simplify this as probability rain, probability traffic rain, and probability umbrella given rain, right? So you see here, to represent these probability values, we needed two variables, right? So we are conditioning umbrella over traffic and rain. So that means traffic and rain can be having true and true, true and false, false and true, true and true. And for each of them, we'll be having probability umbrella given traffic rain, right? So what does that mean? We have 2 to the power 2 assignments. But as soon as we simplify these as probability umbrella given rain, what is the kind of table that we'll be talking about? We'll be talking about only one variable. So either it is true or false. And for that, you have a value probability umbrella given rain, and we'll be having some value. So here, how many assignments we are making? We are making only 2 assignments in the order of 1, right? So we are having very small assignments here. So that's what I'm trying to say, right? So let me revisit the Bayes rule, which I have talked about in bit more detail in the review lecture, and that will be kind of basis of the Bayesian network. So what we did there, we have one hypothesis H and one evidence E, right? So you're computing the probability of hypothesis given evidence, and that can be rewritten as probability E given H, probability H divided by probability H, which we have talked about earlier, right? Now let us try to relook at to see whether it can model the causality. So what we mean by causality? So you have two events, X and Y. So whether X causes Y, right? So for example, whether smoking causes, say, lung cancer, something like that. So there is a causality we want to model using this base rule. Let us try to see whether we can do that. So can we rewrite this in a form like this? So we say that the probability of a cause given effect equal to probability effect given cause, probability cause by probability effect. So this should be effect, right? So let us try to see an example and uh, make out of this something, right? So we are trying to find the probability whether there is a fire given the alarm was ringing, right? So this is what we want to find. Now, how we can find that? We can rely on the probability value, probability alarm given fire, and probability alarm, right? So these are your prior probabilities. So these you get out of your prior data, like say how many times the building has caught fire, something like that, right? Now, how do you get this probability alarm given fire? So what does that? What does it say? It says what is the kind of chance that the alarm rings whenever there is a fire. So this value. So which value is easy to get? This or this? Can you tell me? Which value is easy to get? This one. So I mark this to be 1 and this to be 2. Which one is easy to get? So 1 is easy to get. So basically, if you think about the maker of the device or the alarm device, they will be providing you some data about the sensitivity of the device. So how many times it will ring if there is a fire. So this is a kind of trustworthiness that you have on your device. But this is the kind of dynamic event. So there is a fire, there might be fire or there might not be fire. The incident is that alarm has rung and you want to predict whether there is a fire or not. The alarm may ring based on different situations. Maybe someone has tempered the alarm, so that's why it may be ringing, or the alarm is malfunctioning. That can be another reason there is a kind of false alarm that is set off. But there might be fire or there might not be fire. So you want to diagnose the kind of cause for which an effect has happened, right? So that's why these kind of probability is called a diagnostic probability, right? Now with this, let us define what do we mean by Bayesian network. So what we have seen earlier, that even though we have got plenty of variables in our knowledge base or in our domain, for a given random variable x, there is a very small set of variable. They may directly affect the value of x, right? So whether there is a fire or not, it may be dependent on, say, whether someone is lighting a cigarette inside the building or not. But it may not be dependent on whether someone is taking a printout or not, or someone is writing a code or not, right? So these are kind of independent of the random variable that there is a fire in the building, right? So the direct consequence, or another way of saying this, is that x is conditionally independent of other variables given the value of the directly affecting variable, right? So I know that there might be a fire given that I know that someone has lit a cigarette or not inside the building, right? But it will be independent of the other variables, like someone is taking a printout, right? So if we know the values of the directly affecting variable, then the one random variable is conditionally independent of the other variables. So for example, we have uh, taken this x to be fire. The other variables, they are like someone is taking a printout or not. And directly affecting variable is like someone has lit a cigarette or not, right? So we can encode these kind of information in a graphical structure. So we say by this graphical structure, what we are saying that these are all random variables and the random variable of our interest is xi. And if we know the value of xj, xk and xm, which are directly affecting the outcome of xi, then xi is independent of other variables. That's why they will not be represented in a directed edge like this. So whenever we see that some variable is directly affecting the outcome of another variable, we have a directed edge from that node to the other node. So here in the Bayesian network, we are representing the random variables as node and their interactions as the edges, directed edges. So that's what gives us the Bayesian network. So if we now say what a Bayesian network is, the Bayesian network is a kind of graphical representation of the conditional dependence among a set of variables. So that's what we can get out of this structure, right? Now let us try to define it more formally in graph theoretic form. So I'll be doing that in a bit, I think in the next slide. So we know the chain rule. So we can define this joint distribution to be this, right? So this is a kind of representation of the chain rule. We can have a closer look at it and see. Now what we have, we defined the parent of xi. So this is your xi and these are your parents. These are the parents of xi, right? And this parent of xi is basically, so if we try to kind of order the variables from x1 to xn. So let us try to define order of the variables from x1 to xn, right? Now let us try to see the parent of xi, right? So the parent of xi would be a subset of the variables that are preceding xi, because we have defined the order here. So x1, x2 to xi minus 1. So this is be a subset of this. Why this is so? Because this xi is not dependent on all the variables. It depends on a subset of the variable, right? So that's why we say that parent of xi is a subset of this. Now, as we define the parent of xi to be a subset of this, we can rewrite this formula to be this part. So let me first rewrite this and then rewrite the whole formula. So this part can be rewritten as probability of xi given parent of xi, because I know that the other variables, they are conditionally independent of xi. So they can be removed out of these conditional. So this part is very important. So let me know whether you understood this part or not. So is this okay? Good. So if we assume this, then this chain rule can be written as we are just plugging in this probability xi given x1 to xi minus 1 in this inside this big product, right? And whatever we get this, these are the factors of our joint probability distribution. Now, what is a Bayesian belief network then? How do we represent that? So basically, what we can do, we can represent this xi given parent of xi into a set of these structures. And as we do that, you can see easily that this will become a directed acyclic graph. So it is a directed graph, we know. And also there will not be any cycle in it. And that's why it's a directed acyclic graph, in short, DAG. So this is one property of this Bayesian belief network. And second property is that each node is labeled by a random variable that we have already discussed. And of course, each variable has got a domain, right? So if we are talking about say tooth cavity, etc., they will be belonging to binary domain. But if you say that this is a random variable that represents a roll of a dice, then the domain would be value from 1 to 6, right? But most importantly, every node will be associated with a conditional probability distribution, which is of the form probability xi given parent of xi. So let's say this is your x1, this is your x2, x3, x4, right? So this will be having a kind of conditional probability distribution, and the conditional probability distribution will be represented in a form of a table. And what are the entries of the table? So we have x2, x3, x4. These are the choices, right? So we can have multiple choices on those. And for each of these choices, we have probability x1 given x2, x3, x4, right? So this is the kind of table that we will be maintaining for every such node, right? So what are the contingencies that we have? We have got say true, 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 and we have a probability value here. We have true, true, false. We have a probability value here and something like that. And you have three variables. We have got 2 to the power 3 entries in this particular table, right? And for each entry, each assignment, we have a conditional probability, and that will be representing probability xi given parent of xi, right? So let us take an example and try to make the idea more concrete. So the example that we are taking is a kind of fire diagnostic assistant. So what does it do? It tries to check whether there is a fire in the building based on certain sensors that it has, but the sensors, they might be noisy. So let us see what are the sensors. So one sensor is a report sensor. So there is a reporter which reports whether there is a kind of bulk movement out from the building, right? So whether everyone is leaving the building or not. Now, as it is a kind of noisy sensor, we might be having false positive. So what do we mean by that? So maybe it is reporting that, well, many people are living, but it might be the case that people are not living in that way, right? So it might report people living falsely. Or there might be false negative where people are living, but it does not report, right? Because it is noisy. So there is a fire alarm which goes off when many people live together, right? So this is the kind of characteristics of the fire alarm, right? And also, if there is a tampering or there is a fire, then it can affect the alarm, right? And finally, if there is a fire, it can cause smoke, right? So these are the kind of three sensors that we have with us for this diagnostic agent, right? So from this, we can easily draw a Bayesian network. So for this very simple domain, we can do this readily, but if you have a complex domain, you have to put a lot of effort to design the Bayesian network or the structure of the Bayesian network first. So what we can say that alarm, whether the alarm will go off or not, that depend on tampering and or on fire, right? So either tampering can affect alarm or fire can affect alarm, right? Fire can cause smoke, and if there is an alarm, many people might be leaving the building. So alarm causes people to leave, and if many people are leaving, then the reporter can report the event, right? So you see the dependencies are very simple, right? Now try to see what are the kind of conditional probability tables. So as we have mentioned earlier, that in every node, with every node, we'll be associating a structure xi given parent of xi, right? And that will be doing with a table which we call as conditional probability table or CPT, right? Now tampering, let us look at tampering. Does it depend on anything? It does not depend on anything. So that's why we do not have any conditional. This parent part will be removed. We'll just be having the simple probability of this tampering, the probability of tampering, right? So you know the probability of tampering to be say 0.002, and the probability that there is fire is 0.01. Again, this is not having any parent. Now, how will this alarm CPT for alarm will look like? So as it depend on two variables, we have two two variables in the we can vary the value of the two variables, this tampering and fire, and we have to report the probability of fire given there is tampering, sorry, alarm given tampering and fire, right? And how do we do it for smoke? So we are saying that it is dependent only on fire. So that's why you are having a single variable here, right? And this fire can take a value to be true or false, right? So we are specifying that whenever there is a fire, the probability that there is a smoke given there is a fire is 0.9. So what does it say? The probability of smoke given there is fire. And we are setting this to be a high probability 0.9, right? And probability of smoke when there is not fire, which is 0.01, right? Now you may ask, what happens to the other probability? What is the other probability? The other probability is there is not smoke given fire is true. So can anybody tell what would be the value for this? There is no smoke even though there is fire. What would be the probability value?
0.
Okay, someone is saying 0. Any other idea?
0.1.
It will be 0.1. So this is implicit. So we are saying if given fire. So this is 0.1, right? And the other one would be 0.99. So as knowing this value will reveal this other value, we are not representing that because we want to have our network to be very compact. So this is one difference that we have for the CPT and JPT. CPT is conditional probability table and JPT is joint probability table. In the joint probability table, the probability column will always add up to 1, right? But in CPT, the individual row should be having the total probability to be 1, right? But this column should not be added to get 1. So this is one difference that you should always take care of, right? Similarly, we can define the CPT for alarm. So we have got tempering and fire, and we assign different values to it. And for that, we decide what is the probability value. And the complement probability of this would be 1 minus A, 1 minus this. This will be 1 minus 0.85, something like this, right? And you can easily come up with the CPT for living. So it will be, yeah, this is fine. Living, and this will be the CPT for report, right? So now one might ask, if we do this, what is the benefit? So can you now guess what is the benefit? So what we are interested in? We are interested in probability T, F, A, S, L, R, right? So what is the benefit that we are getting out of this structure? Any idea? Any guess? Well, what is the kind of number of assignments if we want to fully assign this, fully describe this JPD? What is the total number of assignments?
2 to the power 6.
2 to the power 6. Actually, it will be 2 to the power 6 minus 1, isn't it? Precisely. Do you agree? Hello?
Sir, I'm not able to understand why.
Oh, okay. So let's say, so what you have? These individual probability values will be adding up to 1, right?
Yes, sir.
Now you get it?
Okay, sir.
So tell me who hasn't got it? This exact number of assignments. So if we say, let's say we have this 2 to the power 6 equal to n. Let us assume this, right? Now, if I know the probability values of n minus 1 assignments, the nth assignment will be getting just by doing this 1 minus sum over these probability values, isn't it? So that's why we need to have this 2 to the power 6 minus 1 assignments. Now, how many assignments we are getting here, doing here? For this, we are doing only one assignment. For this, we are doing only one assignment. For this, we are doing 4 assignments. For this, 2. This 2. So how many? 4, 8, 12, right? And 2 to the power 6 minus 1 is very, very large with respect to 12. So this is the kind of gain that we are having here. But the point that we'd like to ask, whether it is able to represent the joint distribution or any other kind of probability values that we want to compute out of these structure. So let us try to see whether we can do that. So I have to compute the probability that there is tampering, there is no fire, alarm is ringing, there is not a smoke, people are living, and reporter is saying that the report is true that people are living, right? So I can do it for any other assignment. So let us take this assignment and try to find out the joint distribution, right? So how do we do that? We can use the chain rule, and of course we'll be using the conditional independence assumption also, right? So we can say probability of tampering equal to true, right? Multiply probability fire equals to false. Fire does not depend on any one, so that's we are just writing this probability fire given F, fire F equal to F. Alarm depends on 2 variables, fire and tampering. So that's why we will be writing this factor as alarm is equal to true given P equal to T and F equal to F, right? Smoke depends on only fire. So probability smoke equal to false given fire equals to false, right? And probability living, right? Living depends on what? Alarm, right? So living T alarm equals to T multiply probability report equal to true given living equals to true, right? Now we know what is the probability of t equal to true, which is 0.02, right?
Sir, I have a doubt.
Yes, yes, yes.
Sir, here probability of A equals to T given tampering and tampering is to and fire equals to false. So in this case, should we not write only T and F in the latter part, because true tampering equals to true and fire equals to false is also probabilistic.
Okay, so I understand your doubt. So here you see that we are already setting. So you want to know exactly the case where tampering is equal to true and fire equal to F. So this value we already, so this is the value that we are trying to compute. I'm not interested in other values. So that's why they will be conditioned on the instantiated variables.
Okay, sir.
Okay. So probability of F given F is 1 minus this, right? So it will be 1 minus 0.01, right? And what will be this probability AT given T equal to T, F equal to F. T equal to T, F equal to F. So these values. So 1 minus these values. No, this will be only 0.85, right? S F F given F. F given F. So this so this value, but 1 minus this value, right? 1 minus 0.01. And what would be this probability LT given AT? So LT AT. So we'll be looking at this, right? This value, is this okay? It will be 0.88 and probability RTLT. RTLT is 0.75. So now we see that I can compute any assignment of this. So if we can do that, we can fully specify this probability T, F, alarm, smoke, living, report. So our job is done with lesser number of assignments, of course. Now, can we compute the probability of smoke to be true? So in order to do that, we know that we have a conditional, right? So we can say that probability smoke given fire. So this is the probability that we have specified, but we haven't specified this. So how to do that? So basically what we can do, we can see this to be equal to probability smoke given that there is fire. So I'm writing plus smoke. That means smoke is true. Given fire and probability plus smoke given, sorry, probability smoke, not fire. Right? If we add this up, then we'll be getting probability of smoke. Right? Now, how do we get this? This is a joint distribution, which we can write in a chain rule. So it will be probability of fire multiply probability of plus smoke given plus fire. And how do we write this? We can write this as probability of minus fire multiply probability of plus smoke given not fire, right? We know this, right? This value is 0.01. We know this from the earlier table. Smoke given fire. Smoke given fire is 0.9, right? 0.9. What would be this? It would be 1 minus 0.01. And what is this? This would be probability of plus smoke given not fire. Probability of plus more given not fired is 0.01, right? So you can get this value. So similarly, we can compute the value of alarm. We can compute the value of probability leaving. All these things we can do. Maybe I'm leaving this you to work on this, right? This is another example. This is I think most celebrated example in illustrating Bayesian network in different textbooks, which is a kind of scenario where if there is a burglary or there is an earthquake, the alarm can go off. If alarm goes off, John may call or Mary may call. So this is the kind of network. The network is very easy to visualize, so that's why it is used widely in different examples. And of course, these are the CPTs associated with individual nodes, right? So while we are constructing a Bayesian network, so we need to keep something in mind. So I'm not going to discuss about the issues related to construction of a Bayesian network in detail, but there are certain cues that we will always think about while we are trying to design a Bayesian network or construct a Bayesian network. So the first one observation that you can make here, that the direction between these Mary calls and alarm and John calls and alarm, they have been reversed. So it is saying that if Mary calls, then the alarm set off. If John calls, then the alarm may set off. So which is not a really good way to represent the dependency between these two random variables. This is one thing. The other thing is that there is a kind of dependency between when Mary calls, then John calls. And this is not really something that you can see in the real world. So these, again, is not a very good choice. And again, something that we have revised in the other structure, where we are saying that when there is an alarm, then there is a burglary. When there is an alarm, so there is an earthquake. Again, that is not a very good way to represent. So we need to be very careful about the dependencies, and that is being represented as the directionality of the edges. So that is one thing. The other thing that you can see in this other network, even though your maybe your directionalities are right, but you should not unnecessarily connect different variables. So if you do that, what will happen? Then it will make the number of assignments to be increased. So you have increased number of assignments. So for example, here, burglary is having three parents, right? So as it is having three parents, we'll be having a kind of CPT where we have got three variables here. So three variables here, like say Mary calls, John calls, and say earthquake, and you have a probability of burglary given all this, right? So you are unnecessarily increasing the parent set, and as you are doing that, you are making an increased number of assignments, which is not really very wise to do. So these are the kind of few things that you always should consider while you are designing your Bayesian network. So be very sure about what are the dependencies. Maybe you need help of a domain expert to see whether the dependencies are valid or not. Then you can model that in your Bayesian network. So let me stop at this point. I have a little break of 5 minutes, and then we'll start talking about the relationship between conditional independence and different interesting topologies in the Bayesian network. So yeah, so at this point, if you have any doubts, I'll like to clarify. Otherwise, we can have a break for 5 minutes.
Sir?
Yeah, sure.
Can you go to the slide where you calculated alarm probability?
Okay, sure.
Yeah, here.
Yeah,
So
sure.
this 0.5, how it comes?
So these are kind of
Experiment.
yeah, exactly. So these are empirically driven or maybe provided by domain expert. So
Okay.
so there is a kind of whole body of literature which tells you how to really do that.
Got it.
Yeah, I will be having a break.